Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis through a counterflow heat exchanger using ANSYS Fluent fault tolerant meshing. This is the model. We're having two different fluid domains. This is the inlet of hot water and this is the outlet. Similarly, from right side, this is the inlet of cold water and this is the outlet. Right? So it is a counterflow heat exchanger. So hot water and cold water will be flowing in opposite directions. Right? Okay. To understand the geometry in a better way, let us have a segmented view of this model. Let us cut it from a specific planes. We can cut it from this plane. Let us see. We can understand this one very clearly. This is the inlet of hot water. It will be passing through this way and finally it will come down from this opening. And from this opening, we will provide cold water and this is the exit of cold water. Right? The object should be saved with the extension of FMD or FM database. We have already saved this one. So let us close this one and we need to start Fluent Launcher right now. Starting Fluent Launcher from here. First of all, we need to start fault tolerant meshing. Then we need to import that CAD model. Let us import that model with the custom setting on. Next, we need to load it. We need to drag that component into meshing model. Next, from the advanced section, we need to select part and we need to mesh each part separately. So we'll select the object as part so we can mesh different parts separately. Let's copy settings to child objects and finally we need to create meshing objects. You can see this is the model. Next to that, we need to define the type of analysis. It is an internal analysis. So with internal fluid flow analysis and keeping other things as default, let us describe the geometry and flow. In computational fluid dynamics, we need to have a closed geometry. So the different entries and exits should be closed. We're having two entries and two exits. That means four openings are there that to be closed with different caps. Let us select hot water inlet. This is the hot water inlet and zone type will be definitely velocity inlet or mass flow rate, and we can rename this one as cap 1. We're putting cap 1 at the hot water inlet. Let us create a cap and you can see that cap is created. Next to that, we need to create a cap at the cold water inlet. Again, zone type will be velocity inlet and we're keeping the name as cap 2. Let us create a cap at the inlet of cold water. You can see this is made. Next to that, we need to create cap at the exits. First of all, we will create cap at exit of hot water. And in this case, zone type will be pressure outlet as it is the exit. And we are renaming this one as cap 3. Create cap. Let us check it. You can see hot water exit cap is created and finally we need to create cap at the cold water outlet. Right? So we can select cold water outlet here and again in this case zone type will be pressure outlet and we are renaming this one as cap 4. Let us create cap. It is done. You can check it. All the four caps are produced. Now this is a closed geometry. Our model is ready for next operation. Right? Next to that, we need to identify fluid regions. That means different fluid domains are there that to be identified here. Identify regions. We're having two different regions, hot fluid domain and cold fluid domain. Hot fluid will be passing from this outer shell and cold fluid will be passing from the inner shell. Right? And for identifying these fluid domains, we are having different options like centroid of objects, or you can say numerical inputs or offset methods. We'll select offset method here in this case, right? So what you have to do is, we're having different openings. Let us select cap 1. From cap 1, we are providing hot water, right? So we need to provide hot fluid domain from that location. You can see one diamond shaped object is created. The diamond shaped object will be indicating the hot fluid domain. That's why the diamond shape has to move inside, and that can be done using offset. In this case, it will be y offset. Let us provide y equal to -20, as it is in the negative direction of y. And see that diamond shape is moving inside. Let us provide the value be -50. And the diamond has moved inside. We can check it from clipping planes. You can see here, this is the location of diamond, which is indicating hot fluid domain, right? So we can rename this one as hot fluid region and identify this region. This is identified. Next to that, we need to identify cold fluid region. So we need to select cap 2. And in this case also, we need to provide the method of offset. That means that diamond shape has to move inside, and that will be done using x offset. It will move in the negative direction of x. We are renaming this one as cold fluid domain. And let us provide offset value of x equal to -50. So the diamond shape has moved inside. It is indicating cold fluid domain. Let us identify this region. So we have identified two different fluid domains, hot fluid domain and cold fluid domain. Excluding that one also, we need to identify some void domain which is required to restrict the flow of fluid from inside to outside. Now we'll select void domain, and we're renaming this one as void region. That will be done using offset methods. That means the diamond shape has to move outside this geometry, right? Let us select the whole object, and diamond shape is at the centroid of this counterflow heat exchanger that we moved outside this domain. That can be done using y offset. Let us provide y offset to be 200. Diamond shape has moved outside this domain, which is indicating void domain. Let us move this one a little bit higher. Let us make this diamond shape to be 250 mm away. So this is indicating void domain. Let us identify this region. So we have created three different domains: hot fluid domain, cold fluid domain, and also void domain. Excluding this one, by default another domain will be created, that is solid domain. As it is a heat transfer analysis, we need to consider that solid domain also, right? Next to that, we need to define leakage threshold. In our model, we are not having any kind of leakage, so we can move on with no leakage condition and update this. You can see here, as told before, we are having four different domains. Out of these four domains, cold fluid, hot fluid, and void region, we have already made, and by default it has made another void domain, that is the solid one, that to be converted as solid. We are converting this void one as solid one. Counterflow heat exchanger, that is our model, which is showing as void domain, that to be converted as solid domain. As it is a heat transfer analysis, we need to consider the solid domain also, right? And as I told before, each part of this model we can mesh differently with different meshing options. What we'll do is, we're having two fluid domains, cold fluid and hot fluid. In both cases, we'll consider polyhexacore mesh. And for solid region, that is counterflow heat exchanger, we'll consider tetragonal mesh. And we need not mesh void region. Let us update this region. Next to that, with default mesh control options, let us update this one. Next to that, we need to generate surface mesh with the target skewness as 0.8, and from advanced sections we need to consider separate contact pairs, so it will be yes, and global minimum we are considering 1. Let us generate surface mesh. We can see surface mesh is generated, and different boundary types also can be viewed at the left hand side. You can see we are having two velocity inlets, that is the inlet of cold water and hot water. By the same time we are having two pressure outlets, that is the exit of hot water and cold water, and finally we are having different walls. All these walls are very important. Through these walls it will be transferred by convection. With these different boundaries, let us update. In the next step we need to provide some kind of boundary layers. Let us decrease the numbers of boundary layers. Instead of 3, we will make it 2 numbers of boundary layers, and let us update with 2 boundary layers. Next to that, we need to generate the volume mesh, and in this case we are considering quality improvement limit as 0.04. Let us generate volume mesh. You can see volume mesh is generated, and overall summary is saying that quality less than 0.1 is 1 and quality less than 0.04 is 0. Minimum quality is 0.79, and finally cell count is 72,928. We can check the quality of mesh from here also. Mesh quality is telling that minimum orthogonal quality is 7.89 into 10 to the minus 2, and maximum aspect ratio is 1.89 10 to the 1. That is good enough. So with this mesh quality, let us switch on to solution mode. Now we are in solution mode. First of all, we need to select units, and we'll consider length as millimeter, and we'll consider temperature as degree centigrade. Let us close. It is a steady state analysis, and definitely gravity will be involved, and the direction of gravity is indicated by this green arrow y. So along y direction, gravity will be minus 9.81 meter per second square. Next to that, we need to select models, and as it is a heat transfer analysis, so energy equation should be on. And it will be K-epsilon turbulent model, realizable and scalable wall functions. Next to that, we need to select materials. In this case, we are having two different fluid domains, hot water and cold water, but basic fluid will be water only. We need to provide water from two different domains at different temperatures. So we need to consider basic fluid as water, and that will be obtained from Fluent database. Let us select water. Copy. And next to that, for solid material, we are considering copper. That can be obtained from here, solid, copper, copy, close, close. You can see here that solid material is copper and fluid is water. Next to that, we need to identify cell zone conditions, that is different fluid domains to be identified here. Both the different domains should be made up of water, and actual temperature should be provided during boundary conditions. Cold fluid domain, it will be containing water, water liquid, apply and close. Similarly, hot water region also, it will be water, apply and close. So fluid domains have been defined. Next to that, solid domain should be defined. Solid domain means the whole body, it will be made up of copper only. Let us apply and close. So the fluid domains and solid domains are defined. Next to that, we need to apply our boundary conditions. We are having two inlets, that is inlet of hot water and inlet of cold water. Cap 1 will be providing inlet of hot water. So we can provide that hot water velocity as 0.01 meter per second, and temperature will be 100 degrees centigrade. Apply and close. Now for cold water inlet, we'll provide cold water with a lesser velocity. Let us provide velocity of cold water should be 0.001 meter per second, and temperature it will be 30 degrees centigrade. Let us apply and close. We need to check the outlets. We are having two outlets, that means outlet of hot water and outlet of cold water. At both the outlets, pressure should be equal to 0 gauge pressure. We're considering hot water outlet as cap 3. It should be having 0 gauge pressure. Apply and close. Exactly same way. Cold water outlet, that is cap 4. This one should also be the same boundary condition, that means 0 gauge pressure. Apply and close. We need to see the walls. We're having a lot of walls. Let's consider one. From all these walls, it will be transferred through convection, and we need to provide a specific convective heat transfer coefficient. Let's consider the material for these walls as copper, and from these walls it will be transferred by convection, and we are considering convective heat transfer coefficient to be 50 watt per meter square degree Kelvin at a temperature of 40 degrees centigrade. And let us consider wall thickness as 0.01 millimeter. Let us apply. Now the same boundary condition to be applied for the remaining walls. So what we'll do is we'll copy this boundary condition and that to be provided for the remaining walls. Let us copy the exact boundary condition to the remaining walls. Let us copy. So the exact same boundary condition was applied to the remaining walls also. Close it. Next to that, we need to select solution methods, and in this case we are considering coupled method, and for special discretization we'll consider Green-Gauss node based method, and it will be second order upwind. Next to that, we need to start initialization. Let us start standard initialization, and it will be started from all the zones. Let us initialize. Initialization is done. Next to that, we need to run calculations, and here in this case we'll consider 100 numbers of iterations. Let us calculate. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and analyze. Okay, we can see calculation is complete. Now we can see our results, and results can be viewed from here. And initially you want to see results from reports. It will be surface integrals, and report type it will be facet average. First of all, we want to see temperature at different openings. Temperature at the inlets are known because from hot water inlet we have provided water at 100 degrees centigrade, and from cold water we have provided water at 30 degrees centigrade. We need to see the temperature at the exits of hot water and cold water. Cap 1 is indicating the inlet of hot water, which is 100 degrees centigrade. Cap 2 is inlet of cold water, which is 30 degrees centigrade. These are already known from the boundary conditions. Now cap 3 is the exit of hot water, and cap 4 is the exit of cold water. Excluding that one, we can find out other things like hot outer surface, and you can say temperature at inert solid surface and inert solid surface fluid regions. Let's compute. It is showing that temperature at cap 1 it is 100 degrees centigrade, cap 2 it is 30 degrees centigrade, and cap 3 that is the temperature at the exit of hot water it is 89 degrees centigrade. So its temperature has fallen from 100 degrees centigrade to 89 degrees centigrade. We got a reduction in temperature of approximately 10 degrees centigrade, and for cold water that much of increase we didn't find. Temperature of cold water has risen by only 1 degree approximately. Initial temperature of cold water was 30 degrees centigrade. Now here we can see temperature of cold water at the exit is 30.92, that is approximately 31 degrees centigrade, right? And we can see other things like hot outer surface temperature is 39 degrees centigrade and inner solid surface temperature is 39.99 degrees centigrade. Net temperature is 40 degrees centigrade, right? If we vary the mass flow rate or velocity from different entries, then this temperature can be varied, right? Next one, we want to see different contours of temperature, pressure, velocity, etc. at different regions and also through different planes, right? Let us close it. It will be contours, new contours, and we want to see temperature distribution through different locations, right? It can be viewed through hot fluid body, and also we can see through inert solid surface. Through different locations you can see temperature distribution. Let us display. It is showing temperature distribution through different locations, right? To have a better view, we can make the screen bigger. You can see at different regions we are having different types of temperatures, so it can be viewed in a better way if we see it from different planes, right? For that, what we'll do is we'll create some planes. Let us create some plane surfaces. Along YZ we are keeping one plane, and along XY also we'll create another plane. We have created two different planes. Let us close it. Next to that, we're going to see this temperature distribution through those planes, right? We're going to see temperature distribution through different planes. So contours, new contours, and we're going to see temperature distribution through this plane number 13 and 14. Let us display. So it is clearly visible that temperature at different locations. At the exit level, you can see some different ranges are there. Now we can have a varied ranges of temperatures by changing the velocities or mass flow rate, right? That can be done also. Let us see pressure distribution also through these specific planes. It is better to see different planes separately. We want to see pressure distribution through plane number 13 only. Let us display. So pressure distribution through these planes. See, outside region pressure is a little bit of higher, and inside region pressure is less, which is indicated by different colors. Now what is the pressure distribution through plane number 14? Let us display. At the entry of hot water we are having higher pressure, and at the exit it is having lower pressure. And throughout the cold water pressure remains almost same, right? Next to that, we're going to see the dynamics of flow particles, and that will be obtained from path lines, new path lines, and we're going to see from particle variables, we're going to see temperature distribution in the form of flow particles. Let us see throughout this counterflow heat exchanger. We're going to see all the surfaces. Let us display. it is showing outside it is having higher temperature, which one we have provided at 100 degrees centigrade, and inside temperature is 30 degrees centigrade. It will be better to see in the form of animation. Let us have a pulse of it. You can see how water particles at a different temperatures are moving. Stop and let us close it. Next to that, we need to see is mesh distribution. So here in this case, instead of edges and nodes, we want to see only faces. We want to see only faces throughout the whole body of this contour flow heat exchanger. This is the faces, right? Let us see edges and nodes also display. Next to that, we need to create a scene in between this mesh and also different contours of temperature and pressure. So we need to create a scene. Let us create a scene. It will be in between the path lines and also different contours. And let us make the mesh as transparent. Initially, you want to see the scene between mesh and path lines. Let us display. It is showing the boundaries of hot water. Can make the mesh little bit of transparent. So it is indicating both hot fluid domain and also cold fluid domain, right? Next to that, we're going to see the scene between mesh and contour 2. Let us display. Okay, let's close it. So with this one, we can conclude our today's analysis. This is a very simple analysis of contour flow heat exchanger using ANSYS Fluent fault tolerant meshing. In this case, we could see that temperature of hot water has been reduced a huge amount, but the temperature of cold water was not increased that much. That can be changed by varying the mass flow rate or velocity of different inlets, right? So thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.